Okay, so we're going to talk about continuity. And I think many of you probably have already a good idea of what continuity is. And if you don't, it's actually a pretty straightforward definition. It's that when you're evaluating the limit, you don't have to do any sort of trickiness. All you do is you take the limiting point and you plug it directly into your function, right? So that's the definition. So definition, if f maps D to R, just for some generic domain D, we don't care. And C is a point in D. Then we say that f is continuous at the point C if the limit as x approaches C of f of x is equal to f of C, okay? So if you want to evaluate the limit is straightforward. You just plug C into your function and you get out your answer, and that's what it means to be continuous. Now so there's a couple of important points to make here. So let's say comments. So the first is continuity is a local condition, right? We talk about being continuous at a point. Now, obviously, there will be times when we want to say, well, actually, it's continuous at all the points, right? It's continuous at every point in its domain. And in that case, we'll just say that the function is continuous. So if f is continuous, at every point in its domain, we say that f is continuous. Right, so we don't say it's continuous at a point. We don't say it's continuous at 0 or continuous at pi or whatever. We just say continuous, right? Is it considered as C reachable and there is no limit at C? Well, okay, it depends on what you mean by reachable, right? Because I can't, like, we could interpret that in a couple of ways. So definitely we're saying the limit has to exist, right? Because we're saying that the limit of f of x is equal to f of C. So we're saying the limit exists, 1, and 2, the value of the limit is very special, right? So the limit exists and it is equal to f of C. So we've seen lots of examples where a limit can exist but not be equal to f of C. So the point of continuity is that you can just plug the C into your function and you get the limit point out, right? So in some sense, it's very simple to evaluate the limit. Sometimes, and this kind of fits more with the green comment here than with the red definition, but probably in high school, you've all heard somebody say, oh, well, a function is continuous if you can draw it without lifting your pen from the paper. And there's a sense in which that's true. That describes continuity of the function on its entire domain. This becomes a little bit trickier to understand if we're talking about continuity at individual points, though. And one of the things we're going to do today is talk about a very pathological function, a function which is continuous at lots of places, but then not continuous at lots of places as well. Okay, so that's something that we'll talk about. So does that clear up that question? Because it depends on what you mean by C is reachable. C does have to be in the domain. Like, we're not just going to limit to, right, in order to even evaluate f of C, right, f has to be defined at C. So you can't talk about continuity at, say, a limit or at like a border. Like, so let's say your function's domain is an open interval. We're not going to talk about being continuous at the boundary points of that interval because the function is not defined there, right? So for f of C to actually be defined, C has to be a point in the domain. So I hope that answers the question, but if it doesn't, let me know. And then maybe, clarify your question a little bit, and I'm happy to answer it. How can we evaluate every point to determine if the function is continuous everywhere? So in practice, what you do is you do the epsilon delta proof, but you do it for a generic point instead of a specific point, right? So first of all, we've actually shown that a couple of functions are continuous. So, let me put this as a comment. So 2. So we've shown already the following. So we've shown so that let's call this 2a. If P and Q are polynomials, and Q of C is not 0, right? This is what we talked about before the reading week. Right, we proved that. And that's precisely the statement that any rational polynomial is continuous. So all rational functions are continuous anywhere their denominator is not 0. Right? So this is nice. And if you remember what we did, like this was kind of a buildup of the limit laws, because we first showed that polynomials were continuous and then rational functions. But basically, we did this for every point C, right? We were able to sort of immediately make this argument that this just holds for any point C. And so now we've demonstrated this function is actually continuous. And again, I'll do another one in a second and kind of give you an example, but this is something that we've done, right? For f of x equals x with a domain of R excluding 0, the limit of f of x equal to fc, then this function is continuous, like it has a hole in the point 0. Yes, actually, I would argue that that function is continuous because its domain does not include the point 0. Yes, Stephen. So this is a really great point, and does bring up a lot of conflict because, you know, especially in first year calc, we usually don't consider domains that are disconnected, right? So often our functions are just defined on intervals and they're not disconnected. But Stephen brings up a great point here. So let's say that you're, you know, even make it a little bit simpler. Let's do, you know, the interval -1 to 1, but we take out the point 0. And we just look at the function x on that interval. Yeah, that function is continuous because its domain does not include the point 0. It is continuous at every point of its domain, right? So even though when you graph it, you do actually have to pick up your pen, right? That function is actually continuous. Okay, so does everyone understand that? So Stephen, like, great question, great kind of point. But yeah, it is actually a continuous function. And so what this kind of immediately translates into, which is this great sort of thing that we've hit on, but that we're not going to talk too much about in this course, is that when we talk about continuity, especially if we want to make talk about interesting results, is we often have to talk about the domain, right? Not just the function, but we also have to talk about the domain. And we often have to say things like, well, the domain is connected, right? That it can't kind of be broken into two pieces like you did when you took R and kind of cut out the middle point. Because when you cut out the middle point, you kind of made it into two pieces, right? So an interesting sort of thing that we often also have to talk about, and if you go on and you take second year analysis or any higher level kind of like topology or anything like that, you'll learn that, yeah, we also have to talk about the domain. And we have to talk about special properties. Is it open? Is it closed? Is it connected? Is it compact? Those are all scary words that you'll learn eventually, but we do have to talk about those things as well. Okay. So yeah, first of all, so we've shown that all rational functions are continuous. We've also shown that sine and cosine are continuous. All right, I think we did this at the end of last time. Right? So most of the trig functions are continuous, and in particular, even if you do the weird trig functions like you know, tan or cotangent or cosecant or whatever, again, those are going to be continuous anywhere where their denominators are not 0. And we'll talk about that in a second, that basically the limit laws immediately translate over to give us interesting information about continuous functions as well. Okay, but immediately sine and cosine are also continuous on their entire domains for every real number. So sine and cosine are continuous. Okay, so we've done things like that. Oh, and I guess I should say 3, and hopefully you discovered this when you did assignment 2. The epsilon delta definition of continuity looks very similar to the definition of a limit, because obviously continuity is defined in terms of a limit, but there is actually a small change. So the epsilon delta definition becomes, let me just square myself off a bit better here. Okay, so it becomes for every epsilon, there exists a delta such that for all x and r, now here's the important point. Okay, so 2 changes. So here, obviously, on the right-hand side, where we have f of x minus f of c, obviously we're using f of c now instead of just an arbitrary limit L, because this is our claim, right? Our claim is that f of x, the limit of f of x is f of c. So I'm going to replace the limit with the value of f at that point, right? So that's the first obvious change. Now, a second obvious change, which again, hopefully you figured out in the assignment, is that we actually don't need the 0 less than part before the absolute value of x minus c. Namely, because f of x, the limit of f of x is going to be equal to f of c, now x can be equal to c, right? And in fact, if you drop the 0 less than term, that is equivalent to continuity. Okay, so if you take the whole definition, so yeah, exactly, f of x has to be defined at c, because we were saying it's a point in the domain. Yeah, so to talk about continuity, absolutely, f of x has to be defined at c. And right, this was one of the statements in assignment 2, question 1, with a whole bunch of different epsilon deltas. Do you remember that? So one of the statements was this one, where you drop the 0 less than before the x minus c. That's the same thing as continuity. That's saying not only is your function defined at c, because you can now let the absolute value of x minus c be 0, right? And if the absolute value of x minus c is 0, that says that x can be equal to c. That means that f of x has to be equal to its limit at that point, which, i.e., it has to be f of c. Okay, so dropping this, dropping the 0 less than part, that notation, you know, the symbology there is a little bit weird because I put 0 less than in quotes. But dropping the 0 less than part is equivalent to continuity. Is equivalent to saying that f is continuous. Okay. Now, if there's any confusion about that, you need to say so now, because that's going to be important. We're going to talk about that. But basically, what I want you to do is just think about, hopefully all this can be resolved by thinking about, well, what happens if this absolute value of x minus c is allowed to be 0? Well, if the absolute value of x minus c is allowed to be 0, that means that x is allowed to be equal to the limiting point, right? It doesn't just need to be near the limiting point, which is traditionally what we've done. It's allowed to be equal to the limiting point. And if x is equal to the limiting point, well, we're still going to enforce that f of x has to live in the epsilon band, no matter what size of epsilon band you choose. Well, that forces the limit to actually be f of c, right? So we can still find the limit of an undefined point, but it's not continuous. Yes, right? Like we've kind of done that before. So maybe kind of let me give you a little side thing for that. So this isn't related to the comments, but it's kind of like a little side thing, right? Let's say you take the limit as x approaches 0 of like x squared over x, right? So we know, for example, because we're saying x can't be 0, right? When we actually do this limit, we're saying x cannot be 0, which means I can actually cancel the x's out. And that's equal to 0. If you were to actually plot this function, it would look something like this. right? So in that case, the function is not defined at 0, but we still can find its limit. This is not a continuous function though, right? Because the function is not defined at 0. If I said, if I defined the function to be then it would be continuous, right? Because I defined its value at 0, and moreover actually plugged said what its value is at 0, and it happens to be its limit. Does any delta work when x is equal to c? Not necessarily, no. So what we're saying here is, like, think about this statement. So if I say that the absolute value of x minus c is less than 1, the absolute value of x minus c could be any, we're saying x can be in anything. Or here, let's choose another point. The absolute value of x minus 2 is less than 1. So in that case, we're saying that x is in the interval 1, 3, right? That for any x in the number 1, in the interval 1, 3, f of x minus L is less than epsilon, right? But if I add the 0 is less than x minus 2 is less than 1, then that means that x is in 1, 2, union 2, 3, right? It can't actually take on the value at the point. So it's not that when x equals c, we're choosing different deltas. Remember, we've chosen the delta already. The difference is whether or not I'm allowed to include the number 2 in my interval or not, right? And actually see what the function does. Because here's the thing. Let's say, okay, let's use this example I used for Stephen's question. And let's say that instead of defining the function to be 0 at 0, I let it be 5 at 0, right? So here's the thing. And we talked about this a little bit when we first talked about epsilon delta, but it was very, very quick. Notice that if this is my epsilon band, I'm in trouble because the function actually leaves the epsilon band at 0. Right? The function is equal to 5. That's outside of the epsilon band, right? So when we do a limit, we're specifically saying we don't want to worry about whether the function is badly behaved at the point C. It could be undefined. It could be defined in a really bad way. It could, go off to infinity or do something weird. But we don't care about what actually happens at the limiting point. We're gonna look at everything except for that point and define a limit by shrinking these epsilon bands and correspondingly finding deltas. With continuity now, I'm saying if we say that, yeah, in fact, we have to be able to look at the point at C, then it forces that point to actually live in that hole, right? It can't go off and do something else. If that point does not actually, if the limit is not actually equal to the value of the function at that point, then eventually your epsilon band will shrink to such a point that the value of the function at that point is outside of the epsilon band. I'm getting confused even by the words I'm saying at this point because I'm just saying too many like function and epsilon and delta band. But does this picture make sense? Do you see like why when we, okay, well, I didn't want to do that. Right? Does this make sense? Why when we do the limit definition, we exclude the limiting point? Is everyone okay with that? Right? Because the point to which you're limiting, the function could actually live outside of your epsilon band. So you want to say, I'm going to throw it out, right? Okay. Now, if I say you also have to look at the limiting point itself. And the limiting point itself also has to live in the epsilon band. Then that forces the limit to be equal to the value of the function at that point. And that's equivalent to continuity, right? Because as I shrink this epsilon band, right, in this picture, as I shrink this epsilon band, the only value of the function at 0, which will always stay inside of this epsilon band, is 0, right? Which is precisely what I need to plug that hole. Does that make sense, everyone? Is everyone good though? Everyone's okay? That makes sense? Okay, so this is what I say when we remove the 0 less than, okay, which is this kind of comment over here. When we remove the 0 less than, that is equivalent to continuity. So for comment 3, yellow lines, do you mean that f is continuous at C? You're right, at C. You're right. Thank you. So the actual value doesn't matter. So the actual value doesn't matter in a limit, in an arbitrary limit, but for continuity, the value of the limit does matter, and it has to be f of c. Okay. Is everyone okay-ish with that? Like even just what happens here, let's maybe this will help. So we need that f of x minus L is less than epsilon. Now, no matter what delta you have, if you say that x minus c is less than delta, you can always guarantee that x is equal to c, right? No matter what number you say x minus c has to be less than, x being equal to c will always be less than that because x being equal to c is 0, right? So if you plug that number into here, what do you get? This tells you that f of c minus L has to be less than epsilon for all epsilon greater than 0. And as we were talking about when we proved that limits were unique, the only way this is possible is if f of c is equal to L, right? The only way that f of c minus L, these two constants, are less than epsilon for all epsilon is if they are in fact equal. What do you mean also 0 though? Yeah, you'll have to kind of clarify that a bit. Right? Because like x being equal to c is the same as the x minus c is equal to 0, and that's less than delta for all delta, right? If x is equal to c. Yeah, f of, yeah, exactly. Yeah, because 0 is the only number which is less than epsilon for all epsilon. So the absolute value of f of c minus L has to be equal to 0, which means that f of c minus L has to be equal to 0, which means that f of c has to be equal to L. Exactly. Okay, so does that clarify it a bit? All right, let me maybe zoom out of my comments here. It was a good discussion. I really liked it. And hopefully it's a little bit clear. So we've shown rational functions are continuous, sine and cosine are continuous. And we've talked about the fact that this epsilon delta definition, you drop, and in fact, you have to drop more or less the 0 less than part when you're bounding what x can do in a neighborhood of c. Okay, and like I said, that's actually going to be really, really important. Okay, but it's funny because if you look at the definition of continuity in red at the top there, the definition of continuity looks to be fairly straightforward, right? You're just saying, oh, look, the limit exists and it has to be a very nice value, right? It can't be whatever you want. It actually has to be the value of the function. And yet it kind of leads to this deep conversation. And that's fair. Continuity is not an easy thing. It is not an obvious thing. There's a sense in which I think a lot of people take continuity for granted, but yeah, it's tough. And it's tough in part because it's not actually an analysis concept, right? Like we're doing analysis right now. We're going to talk about differentiability and things like that, but there's a real sense in which continuity is not an analysis concept and that it actually doesn't, it's not native to this study. It's complicated. I'll explain it maybe next year if you come take 257 with me. Okay. Or I can try and explain it more later, but we'll see. Okay, so let me try and answer Vasilos's question a little bit more. Like, how would you show that a function is continuous in general? What you would do is you do something like the following. Actually, here, yeah, let me just say, so the function, and I'm going to be a little bit sloppy here because I'm not specifying a domain, but the function, the nth root of x, is continuous on at any point on which it makes sense. And here, I mean, n is a natural number. Okay. And I guess I could do integer. Let's start with a natural number now. Okay. And so the reason why I've said any point in its domain, because you probably know if n is the square root of x, right? If n is 2 and you're talking about square roots, well, you can't plug negative numbers into the square root function, right? If n is 3 though, and the cube root, well, that function is defined on all of r. So basically what I'm trying to say here is if n is even, we're going to take the interval 0 to infinity. And if n is odd, we're going to take all of r, right? So if you want, you could rephrase it like that or just kind of jot that in your little notes to remind you that that's what I'm saying. But I'm basically saying anywhere where this function makes sense and you can write this, you can plug an x into this function and have it not be some imaginary number, then this function is actually continuous. Now, how do we actually do that? How would we prove this? Okay, so what do we want to show? We want to show that the limit as x approaches c of the nth root of x is the nth root of c. For all c that makes sense. Now, what I'm actually going to do, I'm just going to do the proof in general for c greater than 0. Okay, so I'm going to do c greater than 0 here. And then when n is odd, the proof for c less than 0 is almost identical. Okay, so, and the proof for 0 is very straightforward, right? So if you actually want to check the proof for c equals to 0, that one's actually really, really easy. But the proof when c is greater than 0 or less than 0 is actually a little bit hard. So I'm going to show you. But hopefully you can see what we're going to do here is normally we'd say something like, let's show the limit as x approaches 5 of the fifth root of x is equal to the, or of the nth root of x is equal to the nth root of 5. And so normally we'd be working with a very particular c. The only difference now when we're trying to prove continuity is that I'm going to do it also for all c, right? And I'm just going to say, you know, let c be arbitrary and do the proof like that. And in fact, I think I asked you all to do something like this when we first did epsilon delta. I said, show that the limit of ax plus b as x approach c was ac plus b. Same sort of thing, right? That was showing that all linear functions are continuous. So it's the same sort of thing. Okay, so I'm just going to do rough work as usual. So let's take a look at f of x minus our limit point. And I mean, I think we've done a couple of these proofs before, so we're just going to kind of imitate the same sort of thing that we've done there. So I get the nth root of x minus the nth root of c, right? And then we use our usual trick where we basically do a difference of nth powers, but instead of doing it of x to the n minus c to the n, we do x minus c and break it into, well, here, let me write it out. Maybe you'll be like, oh yeah, I remember that. This should be overhead. Right? Now, is that sum freaking anyone out? I suspect it might be. Let me show you what I mean by this. So when I do this, I'm saying like, oh, if I did the cubed root of x minus the cubed root of c. Remember we did something like this? This is x minus c divided by the cubed root of x squared plus the cubed root of x cubed root of c plus the cubed root of c squared. Right, when I did that like difference of cubes, but I did it on x to the c or on x minus c instead of x cubed minus c cubed. Do you remember that? So that's what I'm doing here. That big, long discussing sum in the denominator is basically that just do the factorization of the nth powers. Everyone okay? Okay. All right. All right, so in our usual sense, what we're going to do is we have the absolute value of x minus c. That's good, right? Because we're taking our limit as x approaches c. So that's the thing we want. But this denominator is in our way, and it's kind of annoying. So I'm going to do our usual bounding trick where we're going to make sure that we're in a neighborhood near c. Now I've assumed that c is greater than 0. So this is very nice, because then what I'm going to do is say assume that x minus c is less than c over 2. Now, normally when we do this, we would say assume that x minus c is less than 1, right? Normally when we do this bounding argument, we say assume that x minus c is less than 1. Now here, though, the reason I've chosen c over 2 is because basically if I expand this out, I'm going to get this, right? So saying that the distance from x to c has to be less than c over 2, right, says that I'm going to start at the midpoint c and I'm going to go c over 2 in each direction, right? So if I go c over 2 to the left, that gives me c over 2. If I go c to the 2 over to the right, I'm going to get c plus c over 2, so 3c over 2. Now, the reason why I've done this, c is greater than 0, and now I've got a lower bound on x, which is also bigger than 0, right? And so in particular, x is always positive, c is always positive. So now I can just get rid of my absolute values. So if I call this star, I'm going to say star is equal to the absolute value of x minus c. All right, so I just got rid of the absolute values because everything in this sum is positive. So the absolute value doesn't make any sense. Now x is bigger than c over 2. So I'm just going to replace it with c over 2 everywhere. Sorry, this should be less than. It's actually strictly less than. Okay, I'm then going to simplify the sum in the denominator, and conveniently what I get is, if I write c over 2 to the power of k over n, if I split that up, the c to the k over n and then the c to the n minus k over n combine to just give me c. Like that. Okay. And now this number, so ignoring the c, this sum from k equals 0 to n minus 1 of 2 to this nasty power, that's 1 plus some stuff. So in particular, that denominator is always going to be less than, is always going to be bigger than 1. So if I just replace it by 1, I get that. Right? So as my rough work, so we're going to set delta to be the minimum of c over 2 and c epsilon. And then do the proof. And so notably, the difference here is normally these two numbers do not, they do depend on our limiting point, right? If I take a limit as I approach 5, I'm going to get different numbers than if I take a limit as I approach 1,000. So these two numbers do normally depend on the limiting point, but we don't see how they depend as a function of the limiting point, right? So what we did here is we did this sort of proof. I only did the rough work, but we did this sort of proof by keeping the limiting point general and kind of generic. And in doing so, we can actually now explicitly see how my choice of delta depends on c, depends on my value of the limiting point. Okay? So are there any questions about that? Could you explain how do you factor the c out again? Sure. So in this line here, let me just use a different color so we know it's not part of it. So let's look at the summand. So the summand will be c to the k over n over 2 to the k over n, right? Once I put the exponent into everything, and then I'm going to times that by c to the n minus k over n. So if I multiply the c's together, right? When you multiply like things with a common base, you add their exponents. So k over n. Right? And then the k plus n minus k just gives you n, so I'm going to get n over n. Like that. And so now the c doesn't depend on k anymore, so I can just pull it out of the sum. No problem. C times epsilon. Oh, sure. So once I'm here, so I know that I want x minus c over c to be less than epsilon. So that means that x minus c has to be less than c times epsilon. And that's my delta, right? Because you get to control what delta is, right? Because you're going to say x minus c has to be less than delta. So that's what my delta is. Okay, everyone's good? And so again, you can try this if you want. Now go back, do your epsilon delta proofs, but where you did them before, now try doing them for a generic C where it makes sense, obviously, right? If you're doing a limit at, if you've got a function that kind of like behaves weirdly at a point, then the limit proof probably doesn't generalize nicely. But back in the day when you were first practicing your epsilon deltas, you probably tried on quadratic functions. You did like x squared minus 1. Now instead of limiting to a specific point, limit to a generic point, C. And just repeat the proof. And you'll see explicitly how the limiting point then shows up in your delta, right? So delta does depend on your limiting point. This is going to be important because next week we're going to talk about uniform continuity. So understanding how delta depends on C is actually a really important thing, because eventually we're going to talk about functions that are so continuous the delta doesn't depend on C. Okay. Does that sentence make sense? Does everyone understand what I'm saying when I say that the delta that you choose depends on your limiting point, right? C. And it always does. Like almost every proof that we've ever done so far, it depends on the limiting point. It's just if you don't do it in general, you often don't see how it actually depends on it because you're doing it for a specific limiting point each time you do it. But now go back, try and do it in general and see how the limiting point explicitly appears in your choice of delta. Okay, so hopefully that's okay. And I guess there's something, and again, I'm recording, so even if you wanted that stuff, you just go back, look at the recording. I guess there's something else we should say here as well. I'm going to leave this one as a bit of as an exercise. This one's actually really easy. Okay, so I know there's a lot of dashes and dots here. This is the absolute value function, right? That's what I'm trying to write here. Okay, so this function is continuous everywhere. In fact, it is almost obviously so. Where is the only point you have to check for the absolute value of x? What is the definition of the absolute value of x? Does anyone remember? Okay, yeah, it's distance from 0 and exactly piecewise. And Stephen, yes, exactly, right? Right? So the absolute value of x is defined this way. Now, it's clearly the function x is continuous, right? Because we said all rational functions are continuous. That includes all polynomials. So the function x is continuous. The function negative x is continuous. So, the absolute value function is continuous when x is greater than 0 and when x is less than 0. So the only point you have to check is when x is 0, right? That's the only point where these two things might not agree. So you just have to check that this function is continuous at 0, and I claim that that proof is a joke. It's so easy. Okay, so clearly continuous on R not 0. So just check. So you just have to check that, okay? The limit as x approaches 0 of the absolute value of x is equal to 0. And like I said, if you write out that epsilon delta, you're like, oh yeah, that's real easy, okay? Okay, so now we have a ton of functions which are continuous. We have almost anything that we can think of. The nth roots functions are all continuous. The rational functions, sines, cosines. Oh, you know what? You know what I should say? I should say the limit laws obviously now translate to continuous functions. And I say obviously, but I'll explain what that means. Maybe let me say this in white. Note that the limit laws immediately tell us that the scalar multiple, that maybe let me say that any scalar multiple, a sum of 2, a product of 2, a quotient of 2, okay? So the limit laws immediately, so what when I've written this, I basically just didn't want to write continuous functions as continuous 4 times. So I've kind of summarized it and said a sum of 2 continuous functions is continuous. A product of 2 continuous functions is continuous. A quotient of 2 continuous functions is continuous with a little asterisk on it. Any scalar multiple of a continuous function is continuous, right? Because that's what the limit laws tell us. And the asterisk here is the usual if the denominator is not 0. Okay. And if you don't see what I mean by this, let's do the sum, right? So in the case of the sum, so let's suppose that f and g are both continuous at C. Right? And we want to show that f plus g is also continuous at C. Right? And the limit laws are going to give us this because if I start doing this computation, now by the limit laws, right, I know the limit of f and g both exist, right, because they're both continuous at C. Okay, so this is by the limit laws. Now they're both continuous, so I know what these numbers are, right? The limit of f of x is just f of c. The limit of g of x is g of c. And that is exactly f plus g evaluated at C, right? So yeah, the sum of two continuous functions is continuous precisely because the limit laws lets me break them up and evaluate their limits separately, but I know what their limits are. Same sort of thing, the product, exactly the same sort of thing. The limit of f times g is the limit of f times the limit of g. If they're both continuous, both those limits exist and are equal to f of c and g of c. So boom, the product of continuous functions is continuous, et cetera, et cetera, et cetera. Okay, yeah, this is a good question. What about the composition? The composition is a whole different ball game, right? So we're going to have to do something about that because we didn't talk about how to compose limits, right? Like if I gave you two functions, how do we evaluate the limit of their composition? We didn't talk about how to do that. So that is a great question, and we're going to have to think about it. The kind of hint is, or the kind of sneak peek is that yes, the composition of continuous functions is going to be continuous. But the proof here, I'm going to do it in slightly in an unorthodox way, because there's something kind of cooler that we can prove if we're willing to take a small tangent, right? So we'll come to that probably not until a little bit after the break, but will be the same for F inverse. Okay, this is a complicated question. So the inverse of a continuous function generally does not need to be continuous. However, it will be for anything you can think of. Yeah, so that's true, Yuan-Jie. Like the inverse might not exist, but so let's suppose that the inverse exists, right? So let's suppose that you have a continuous bijective function. So you know that the inverse exists. And now we could ask the question, right? We can say, does the inverse exist? And the answer is yes, as far as you're concerned, but no in general. Okay, and so that might seem like a very cryptic answer because it is. The answer is that for us, for any continuous map, any continuous bijection from R to R will have a continuous inverse, but it is not true. It's not true outside of R. I'm pretty sure this is true. Let me just check this out real quick. So this is called invariance of domain. So invariance of domain is a theorem in topology about homeomorphic sets of Euclidean Rn. It states V is an open and is continuous injective map, then V is open and F is a homeomorphism. Right, okay. So this is the theorem that you want. Let me show you. So this is like I said, this is an actually really complicated question. Now, most of these words I don't think are going to be obvious to you, right? But if U is an open set, you can think of that as kind of being an open interval. It's more complicated than that, but think of it as being an open interval. And just take R1. So if U is an open interval of R1 and F mapping that open interval to R is an injective continuous map, then its image is open. Again, think of it as being an open interval. And F is a homeomorphism, i.e. the inverse of F is also continuous. That's what homeomorphism means. It means its inverse is also continuous. Okay, now, a couple of important points here. This only says injective, but that's because injectivity is all you need to guarantee the existence of an inverse. But let's assume bijective just to make our lives a little bit easier. But bijective includes injective. So if you have a bijective continuous map, then yeah, it's a homeomorphism, i.e. its inverse is always continuous. This does not hold outside of R. Okay, and the reason you might be like, well, why do we care? This is a course in real analysis. As you start to do more complicated analysis and you leave R, this result will no longer be true. So I say this with the following caveat. Oh, and also this proof is insanely hard. So the fact that this is true it is true for anything you will see, but I don't want you to have this idea in your brain that in first year analysis, I told you that the inverse of a continuous function is always continuous. And when you get into third year, you're like, wait a second, my first year analysis teacher lied to me. Okay, just as a caveat for you, yes, it will be. But one, try and prove it. And two, you're not going to be able to, because this proof, you need algebraic topology. So for most of you, that will be grad school before you see this proof, right? Yeah, so yeah, this is, look at how hard this is. This is insane. Exactly. This is actually a great way, Yvonne, of like thinking about this. It was proved in 1912. And most of the stuff that we're doing was done in like the late 18th century, right? So in the 1700s. So that's how hard this proof is. For most of you, you will not see this proof ever in your mathematical lives unless you go to grad school. Okay, that's how hard this proof is. So the answer is, like I said, the answer is yes, but it's not obvious why it's yes, even though it's a relatively simple statement. Okay. That being said, there's some nicer, I think actually the proof, let me think. We can prove it for functions from R to R without much trouble. I think the proof from R to R is not terrible. The big thing about that proof is that it holds for all Rn, right? That proof holds for all Rn. And if the question is only in R, then I'm pretty sure the proof is doable, because you just epsilon delta it. But even then, the proof is not easy. It's not hard. You could do it. I think you could actually do the proof, but the proof is not easy. So that proof, the proof of invariance of domain, uses, like I said, it uses algebraic topology. You need to know about homotopies, cohomology groups. So basically, you need a ton more topology and a ton more algebra. It like that is taught in the, I think the first time that result is proven at U of T is in graduate topology, in the graduate topology class, right? Because that's the first time you have the tools to prove it. That's how hard that theorem is. But we can, and I think I actually will prove it for you. Let me double check here. I know exactly where it would be. But I think we can do the proof in R. But it is, like I said, if I recall correctly, the proof is a mess. And it's not a mess because it's particularly hard. The proof is actually relatively straightforward. The notation is just a mess. And I know exactly where to prove it. F is bijection, blah, 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 blah. So increasing and continuous, you can show, so 2.4-27. So if you go to my, if you happen to have my book, and I know some of you do, exercise 2.4-27, and did I scaffold it? Close. Okay. So yeah, you can show that the inverse of a continuous function, the inverse of an increasing function is continuous, right? That one's not too hard. But the inverse of a continuous function. Yeah, that, let me think about it. Let me think if I can prove it. Increasing is not too hard. The inverse of an increasing function is continuous is not too hard. But the fact that the inverse of a continuous function is continuous might be trickier. Like I said, let me think about it. This is a nice kind of detour. 2.428. Do I say it explicitly in that? For me, it's a periodic. Did I add a question in there? So 2.428 is a question about periodicity. Yeah, but the problem is, so kind of what you want to do in this situation is you want to say, okay, well, listen, if I give you a continuous function, break it into the intervals in which it's increasing, in which it's strictly monotone, right? Break a function into the intervals where it's increasing and decreasing. And then you argue that, look, its inverse on each portion is maybe continuous. And then when you glue them all together, you get a continuous function or something like this. But the problem is there exist continuous nowhere monotone functions. In fact, sine 1 over x is nowhere monotone in an interval of 0. So, or sine x, or x sine 1 over x is nowhere monotone in an interval of 0. So like that doesn't quite work. And then for 2.4-28, we need the function to be periodic, which we don't have in general. So I think the proof for continuous might still be really, really tough. But like I said, let me think about it. Let me see if I can come up with something. The proof for increasing is not hard, but for general continuous, it might actually be really tough. Okay, so like I said, that was actually a really interesting and fun detour where we learned that even first year analysis stuff can be really, really hard. And that there are some mathematical embarrassments in that it took us a lot of power before we were able to prove some things. Yeah, let me see if I can, it's really bugging me because I feel like I've proven that the inverse of a continuous function is continuous from R to R before without using invariance of domain. Let me think about that. Okay, but anyway, now's a good time for a break. When we come back, we'll talk about compositions of continuous functions, and I'll show you a cool little trick that we can do with them. Like I said, we're going to prove it in a slightly unorthodox way. And I hope it's not confusing. I'm going to try and prove it in a way that I hope reads clearly, but let me know if it's confusing. All right, so let's take a 10-minute break here. I've got 10:09 on my clock, so I say we come back at 10:19. But either way, in 10 minutes or so, again, post any questions you have in the chat. I'll be around and I'll answer them. Otherwise, I'll see you in 10 minutes. Resume the recording. Good. And now share. Oops. Okay. So, and this overrode my window. Okay. So the theorem that I'm about to do now, let me just make sure there wasn't anything else I wanted to talk about first. No. Okay. So theorem. I'm going to state this in a weird way, and it's not going to be obvious that I'm talking about continuity in any way, shape, or form here, but just bear with me. So suppose that f and g are functions such that the limit of g of x is L, and the limit as x approaches L, f of x is equal to m. Okay. So what I want to be able to do, notice, okay, so the limit for f of x is equal to L, right? This is important. It's not just a generic limiting point. Yes, the cat, there is a cat in the background. So he's diabetic. He just got his insulin, and so now he's screaming at me. But he'll be quiet eventually. Yes, he's already walked away. He's tired of my ignoring him. Okay, so importantly, this L is this L here. Okay, so keep that in mind. Now, what I want to be able to do is to compose these two functions. Now, I haven't specified the domains of these functions just because it gets a little bit messy, but obviously we need the domains to match up in such a way that the codomain of G is the domain of F, because if I want to even talk about the limit as x approaches L for f of x, then it has to agree with G of x in an appropriate way that I can actually compose these functions in the first place. I want to be able to compose these and say something about the limit of their composition. So if either, so I'm going to give you two cases here. If either one, f is continuous at L, and if f is continuous at L, then in fact, m is equal to f of L, right? Or two, there exists some rho greater than 0 such that g of x is not equal to L, oops, on, or let's say for right? Then the limit as x approaches c is equal to m. Okay, there's a lot to take in here. A lot to take in. Maybe we'll draw a little picture to help us out. All right, so we've got G taking C to L. And then we've got F mapping L to M. And what I want to be able to say is that if I do this composition, F compose G, and I take the limit of the composition function as x approaches C, then I should be able to just chain through the arrows and say that C goes to M, right? So the limit as x approaches C maps to M. Does that make sense? But in order to be able to do that, one of these two conditions has to be true. Now, the problem with proving this theorem is that the proofs are technically quite different depending on which of these cases you take to be true. Because I don't want to write the same proof, because I don't want to write two proofs, I'm going to try and do them at the same time. And hopefully you don't freak out and it's okay and you don't yell. Actually, you know what I want to do? So up here where in the hypotheses where I had the limit as x approaches L of f of x equals m, just to make it a little bit more clear, let me actually change the variable name. Let me change it to y. Okay, just to make it a little bit more clear when I actually write the proof what's going on. Okay, so let me know if this doesn't make sense. I'm going to write the proof for you. So proof. So since, or let's fix an epsilon greater than 0. Since f goes to m, we can find a delta. I'm actually going to call it delta hat. Such that oh, I'm using y's, right? Sorry. Okay, I'm going to call this equation 1. Right, so I didn't do anything. All I did was say, boom, this is the definition of what it means for f of x to approach m as x approaches L. And I called it delta hat. And you're going to see why I called it delta hat in a second. Now, because I'm doing function composition, basically what I want to do is say, okay, I know that g of x approaches L, but instead of using epsilon, right, because I know that limit exists, I can feed it an epsilon and get a delta, but instead of feeding it epsilon, I'm going to feed it delta hat. And you'll see why in a second. So since the limit as x approaches C, g of x equals L, there exists delta greater than 0 such that less than delta hat. Okay. Now, basically what I want to do is almost exactly what this picture in blue here says. I want to almost just chain the implications together. Okay. I'm not going to be able to, though. So what we'd like to do, let me even say that, we'd like to combine these, right? So we'd like to say less than delta implies g of x minus L is less than delta hat. right? Because basically, if I could let y be equal to g of x, which I'm absolutely allowed to do, right? If I could let y be equal to g of x, I would be done. So what I would like to do is somehow combine, make these statements the same, but I can't because they're different. Does everyone see what the issue is? So if I let, for example, y be equal to g of x in the bottom of equation, what do you mean? Yeah, exactly. Well, it is the zero, right? The zero is the issue, right? That I have that zero less than in one line. Like those aren't the same line. If these two things were exactly the same, just with y being equal to g of x, then I could string this chain of implications together and I would be done. I would have 0 less than x minus c less than delta implies f of g of x minus m is less than epsilon, right? But in the yellow box thing that I've drawn, these two statements aren't the same statement precisely because of the 0 less than. Okay, so this thing right here, let me maybe draw it a little bit different. So that's a problem. Okay, or basically just the fact these two things don't agree. So what I need to do is I need to fix it. And there's two ways that I can fix it. So in case one, we have that f is actually continuous, right? So if f is continuous, that's not how you spell that. Then equation 2 here, right? This is equation, this is equation 2 and this is equation 1. Equation 1 actually gets rid of the 0 less than. Equation 1 becomes and so we get 0 less than x minus c less than delta implies g of x minus L less than delta hat. This thing here, this is our y, right? It's the same thing as playing the role of y. Right? So f of g of x minus m is less than epsilon. That's what we wanted to prove, right? Look at you kind of ignore the middle portion of the implication arrows. We assume that x minus c is less than delta. We prove that f of g of x minus m is less than epsilon. Voila, we've shown that the limit of the composition is m, right? So the fact that f is continuous let us get rid of the 0 less than y minus L less than delta hat so that these two equations became the same thing. As you can imagine, case 2 does something similar, but what it actually does, right? Maybe let me remind you of what number 2 said. So number 2 says there's some interval such that g of x is not equal to L whenever x minus c is less than rho, namely that it's going to let me put the 0 less than g of x minus L less than delta hat, right? Because g of x isn't actually equal to L. So in case 2, since g of x is not equal to L, when x minus c is less than rho. So in this case, you would have to modify it and you'd have to say, let delta actually be the min of rho and whatever my original delta was. Oh man, he's come into the room now. Instead of calling it delta, what do I want to call it? Let's call it delta squiggle be the min of delta and rho. So if 0 is less than x minus c less than delta tilde, then 0 is less than g of x minus L less than delta hat. And now I have that 0 less than. And so f of g of x minus m is less than epsilon. Like that. Okay, so I had to actually change the delta that I use. I had to use delta squiggle tilde instead of just delta, but that's fine. I can do that, right? I get to choose the delta that I want. And now I've shown that f of g of x minus m is less than epsilon. Okay. Any questions? So the delta for the two cases are different. Yes, actually they are. Yeah. Because in particular, well, they could be the same. We don't know, right? Because it depends on what rho is. Like what I need, I'm trying to put this, let me highlight it in like red. All right, this is green. So I'm trying to put this 0 less than g of x minus L less than delta here, right? So I need to be able to put that, and case 2 is exactly what I need to be able to do that, but I can only do it if I'm, within a distance of rho from the point C. So it's one of those cases where I need to be both. What do I need? I need this to be true. And then if we go up to the condition statement, I need this to be true, right? So I need both of these to be true at the same time. And the way that I make them both true at the same time is to take the minimum of them, right? Now, if rho is big in such a way that when I take the minimum, that I get the same delta, they absolutely could be the same. Case 1 and case 2 could be the same deltas. But in order to use case 2, I really needed to make sure that I was in that neighborhood rho where g of x was never equal to L. So I had to take the minimum of the two of them. But absolutely, again, you can always take smaller deltas. So there is a sense in which you could force case 1 and case 2 to have the same deltas if you wanted to. I don't think there's any practical reason to do that. Because again, the theorem just tells you that the limit of the composition is the limit of f. So you'll never actually have to find the deltas if you wanted to, but you could just choose delta tilde to be the min of delta and rho from the very beginning in both cases, and then use the same delta in both cases if you really wanted to. Okay, is everyone all right with this? It all comes down to, at the end of the day, this little yellow shoe, backwards shoe shaped thing, right? That one has, y minus L is less than delta hat, and the other one has 0 is less than y minus L is less than delta hat. And we just need to make sure that these two things are the same statement. Case 1 gets rid of the 0 less than. Case 2 adds the 0 less than to one of the statements to make sure that they agree. But either way, we just are trying to slot them together, dovetail them together so that the chain of implications goes through, okay? So you might say like, well, okay, well, why did you prove it this way, right? This seems like a complicated way. So the nice thing about this is that we can immediately prove two corollaries from this. So the first corollary is the one that we were talking about, corollary, and it's that the limit of continuous functions is, or the composition of continuous functions is continuous. Or maybe I should be more precise. So if G is continuous at C and F is continuous at G of C, then their composition is continuous at C, right? So the proof is, we know. So first of all, one of the cases is immediately satisfied, right? So one of the case 1 was that F was continuous at the limit L, which is G of C. So we're in the case of the previous theorem. right? So by the theorem statement, the limit of their composition is f of g of c, but that's exactly what we wanted. All right, because that's exactly what it means for their function composition to be continuous at the point C. All right, so great. Compositions of continuous functions are continuous. There is this caveat that you have to make sure, again, that they line up. You can't just like say if G is continuous at C and F is continuous at C, that their composition is continuous at C. No, you need F to be continuous at G of C, right? Not at C, at G of C. And then the other thing that allows us to do is change of variables. Do change variables. Okay, so let me show you what I mean. So this is the sort of thing that we use all the time in first-year calculus courses, but no one ever proves that you're actually allowed to do this. So as an example, I'm going to show you exactly what I mean by this. And I'm going to do it the long, hard way, but then I'm going to show you the short way of doing it. So I'm going to say find the limit as x approaches 1 of the square root of x divided by, or square root of x minus 1 divided by the cubed root of x minus 1. Okay. Now, no problem. If you want to rationalize the numerator and the denominator, you totally can. You'll get the right answer. It seems like a lot of work to me. So what I'm going to do, and again, this isn't how you would do it in practice, but I'm going to do it using the theorem to begin with, and then use this to justify how we would normally do this. So solution. So what I'm going to do is I'm going to let f of x be x cubed minus 1 over x squared minus 1. And I'm going to let g of x be the 6th root of x, right? And this probably looks a little bit crazy to you, but hopefully it'll make a little bit more sense once I compose these two functions. So that okay, so I'm going to get the 6th root of x cubed minus 1, 6th root of x squared minus 1. And voila, look at what happened. So when I compose these two functions, I got exactly the thing which I'm trying to compute the limit of, right? And I chose the 6th root precisely because 6 was the least common multiple of 2 and 3, right? So I've got a square root, I've got a cubed root. I chose the 6th root because it's the least common multiple. And I know that I could create both a 6th root and a cube root from the 6th root, right? That's why I chose it. So according to the theorem, so we know that the limit as x approaches 1 of g of x, so that's the 6th root of x, but we've already proven the 6th root is continuous, so we can just plug it in. 6th root of 1, which is just 1. The limit as x approaches 1 of f of x, x cubed minus 1 over x squared minus 1. You're probably familiar with doing this sort of thing before, right? Where you say, oh, look, x minus 1 is a factor of both of them. Now, because x isn't equal to 1, we can cancel out the x minus 1s. This is a rational polynomial whose denominator is not equal to 0 at the limiting point. Therefore, it's continuous, and I can just plug everything in like that. Now I need to check that one of my two conditions is satisfied, namely that either f is continuous or that there is a neighborhood, a deleted neighborhood on which g of x is never equal to 1. Now, f is not continuous. Do you all agree? F is not continuous at 1. So I can't use that case. Everyone agrees? Right? The f of 1 is just not defined. In fact, I could actually define it so that f was continuous if I wanted to bypass this, but let's not worry about that. F is not continuous. However, there is a neighborhood on which g of x is not equal to 1, right? In fact, the sixth root of x is injective. So the only place at which g is equal to 1 is 1, right? So case 2 is satisfied. And again, we could define f so that it was continuous, in which case that would be totally fine. Or define f to be 3/2 at x equals 1. So it's continuous. So by the theorem, we have that the limit as x approaches 1 so that's the limit of f composed g. And we found that's just going to be the limit of f, right? So it's 3/2, like so. Now this is called change of variable, but it's not obvious that what I've done here is a change of variable because it just looks like you define this function f, you define this function g, and sure, but like how is that the change of variable that we normally do? So in practice, what you would do is the following. So in practice, what you do is say, we'd set let u be the sixth root of x so that u approaches 1 as x approaches 1, right? Thus, so this is what I'm showing you here is how it's normally written when people do this in like MAT135. Right? And then like we've done that one before, right? Let me maybe just write out very quickly. Like that. So you can see that's significantly less writing, but that's normally the change of variables. And that's how people do that when they're, again, when you're doing like MAT135, they write that in, but nobody ever proves that you're actually allowed to do that. So we've now actually proved that you are allowed to make that change of variables in precisely the conditions under which you're allowed to do that. And those conditions are actually necessary. It is relatively straightforward to construct counterexamples where if f is not continuous and g is not locally, what do I want to say, is not, I don't know if that has a word, but basically if there isn't an interval on which g is never equal to L, then you can break this theorem and it all just comes shattering apart. And in those cases, you actually can't do the change of variables. It doesn't work out. Okay, so but in practice, this is how you would write this. And you're allowed to do this. Again, you should probably make some sort of justification that either the function that you transform it into is almost continuous, is continuous as close as we want, or that the sixth root of x is, there's an interval on which that thing is never equal to 1. And then if you do that, if you make that justification, you can make a change of variables. Okay, so does that make sense? Okay, so that's a nice little trick. It'll help you like help you to actually compute some limits. Again, you can kind of see if you write it out properly, it's way longer than if you just do the change of variables. So, I mean, I'm okay if you just do the change of variables in the future, but again, now you know what the actual theorem is that lets you do change of variables. So you just have to check every time you do it that you're actually allowed to do it, right? Can I explain case 2 again, like from the proof? Or why case 2 is true is satisfied here? Okay, yeah. So you're saying why this case 2 is satisfied? Because I just said it, right? Like I didn't actually kind of justify it. So the 6th root of x is actually injective. So the only way that this is equal to 1 is precisely if x is equal to 1, right? And so certainly if I'm on an interval that doesn't include the number 1, then the 6th root of x will not be equal to 1. So on any interval, around 1, the 6th root of x does not equal 1, right? And that's what we need. So case 2 says, got to go all the way up. Case 2 says, if there is some row such that g of x is not equal to L for all points in a deleted open neighborhood of C, then that's case 2, right? So I just need to show that the 6th root of x, I need to show that the 6th root of x is not equal to 1 on some deleted open neighborhood of 1. But because the 6th root of x is injective, it's actually never equal, like no matter what interval I choose, it's not ever going to be equal to 1 again, right? So the issue that you can run into is if your function oscillates, right, and actually oscillates infinitely often near the point at which you're trying to do your substitution, then you run into trouble. And you imagine that probably doesn't happen too often, but that's the sort of thing that could go wrong, right? Is that your function, you get like a sine 1 over x at 0 sort of thing happening, and then you're in trouble. Okay, cool. And I guess let me just write up the different types of discontinuities, and then that way next time I can just dedicate most of my time to Tomei's function, which is really fun. Okay, so definition. So let's begin by supposing, or, oh, sorry, I missed that. For the limit where we subbed x with u at the end, are the numerator and denominator switched? Yes, you're right. You are right. I did switch these. U cubed, u squared, like that. Yeah, absolutely. Thank you. So suppose that f is not continuous at C. And let's let L plus minus be their one-sided limits, okay? So what I'm saying is that L plus is the limit as x approaches C from the right. L minus is the limit as x approaches C from the left, okay? So L, it's not L plus minus is a single thing. It's actually two different things depending on whether it's a plus or a minus, okay? So one, we say that C is a removable discontinuity if L plus and L minus exist and are equal, okay? It's a jump discontinuity if they both exist but are not equal. a jump discontinuity if L plus and L minus exist, but L plus does not equal L minus. And 3, we say that C is an essential discontinuity. If one of L plus or L minus does not exist. Okay, so you can imagine this is kind of more of a 135 thing where they would give an example to say like classify the discontinuities. It's possible that I might give you a question like that at some point, but more so just so that you understand what words I'm using, right? If I say it's a removable discontinuity, jump discontinuity, or an essential discontinuity, I want you to know what I mean by that. And, we can kind of plot this. So a removable discontinuity is something like this. So this is removable. And the reason why it's called removable is basically, and that point might not actually exist, right? So it could exist, it might not exist, doesn't matter. The point is that there's just this hole in your curve. And it's called a removable discontinuity because you could actually remove the discontinuity. You could make the function continuous just by plugging the hole, right? So if you took that point and you plugged it into that little hole there, then it would become a continuous function, right? So in some essence, you're not really discontinuous. A jump discontinuity, you probably can imagine what that looks like. Right? There's a jump discontinuity. So it's not just that there's a hole, but the two ends actually don't match up. So the one-sided limits exist, but they don't line up. And then an essential discontinuity. Actually, I can make this a little bit shorter. Is everything else. So it could, for example, be something like this. I guess I should draw in C here as well. Right, so that's an essential discontinuity, right? Even though the limit from the left exists, the limit from the right doesn't, right? Shoots off to infinity. Sine 1 over x also has an essential discontinuity at 0, right? Because it oscillates infinitely quickly. There are lots of ways that you could be essential. So it's not just that, for example, the limit goes off to infinity, you could oscillate infinitely quickly. There's lots of things you can do. Basically, an essential discontinuity is any discontinuity that isn't removable or a jump discontinuity, right? So all the other discontinuities are essential. Okay, so kind of like in this example above here in the white, where we had u cubed minus 1 divided by u squared minus 1, that function is not continuous, but its discontinuity is actually removable, right? Same thing actually with square root of x minus 1 and cube root of x minus 1. That function also has a removable discontinuity because the limit, right, the two-sided limit actually exists. It's just the function's not defined there. So if we plug that hole, then the function actually would be continuous. So that's a removable discontinuity. Jump discontinuity, you imagine it's easy to create with like a piecewise function, but we also know that x divided by the absolute value of x is a jump discontinuity, right? I think we've seen that function before, so we know it's a jump discontinuity. And then anything with a vertical asymptote is an essential discontinuity, right? Or sine 1 over x. You're all showing in this assignment, sine 1 over x doesn't have a limit as you go to 0. So neither L plus nor L minus exists. That discontinuity must be essential, right? So we've seen examples of all of these sorts of things. And now this is just us classifying them so that we can talk about what exactly they are. Removable discontinuities, like I said, easily fixed, plug the hole. Jump discontinuities are a little bit trickier as you kind of have to like vertically translate each part to the left and the right of the discontinuity, that's going to actually show up a lot when we do integration. And then essential discontinuities, well, you're SOL, right? You're out of luck because it's so badly behaved. There's no amount of finagling you could do to the function to try and fix it. You're just screwed. Okay, so does that make sense? All right, so when we come back next time, I'm going to talk about Thomae's function. Now, as just kind of a fun little exercise, what I'd like you to try and think of is, this is what Thomae's function is. It is a function which is continuous at every irrational number and discontinuous at every rational number. Okay, and it would be interesting to see, well, no, I'm not going to tell you how to spell it because then you can look it up. But because the exercise I want to give you is to see if you can come up with it for yourself. Okay, can you think of a function which is continuous at the irrationals and discontinuous at the irrationals? Or sorry, continuous at the irrationals, discontinuous at the rationals. Let me put that in the chat. So continuous at the rationals, discontinuous at the, yeah. Even when I type it, I screw it up. Okay, so see if you can come up with such a function and then see if you can prove it. And that I think will be a fun little exercise. And we'll do it. I'll actually show you the function and then we'll prove it when we come back on Thursday. All right, everyone. Okay, that's going to finish it off for us. I'll hang around for a little bit in case anyone has any last minute questions. Otherwise, I'll see the rest of you on Thursday. I mean, I don't know. Maybe I can turn it. He's on the bed, right? You can kind of like see a bit of him. He's finally quiet, so I don't want to like go wake him up. So he starts meowing again. Thank you. Thanks, everyone. See you in a bit. You too.